So good morning, everyone. So I'm going to talk today about optimization using Gaussian processes, and in particular, constraint optimization. So here is the outline of my presentation. I'm going to describe quickly the context, which is metamodel-based optimization, and then propose you a new framework for optimization, which is stepwise uncertainty reduction, and then how I adapt it to the constraint optimization case. So the context of my work is the one of design of analysis of computer experiments. So I'm quite happy to be here at the IAStat conference because I'm more from the computer experiments community, and we have done a lot of things quite similar to artificial intelligence community, and there's sometimes a lack of communications between the two. So, but we do a similar work. So my context is the study of black box models, so typically finite element code or something very expensive to compute. That depends on a set of inputs, say X, of a relatively small dimension for me, say below 50, and with a couple of outputs of interest, which I decompose here between an objective, which I want to maximize or minimize, and a couple of additional outputs, which I consider as constraints. So the optimization problem that often arises is that you want to maximize one quantity, say the performance of your system, and you want the other outputs to stay between some bounds or thresholds. So typically you have a performance and you have a cost or an impact, ecological impact, or a risk, whatever. So the problem is, for simplification, minimization always of f. And I have these constraints, which are nonlinear. And the big problem is that this box is very expensive to compute. It takes, say, 1 hour or 1 day to compute. So I have to choose very wisely my set of inputs x sequentially to find the minimum of this function. And I don't want to spend too much time on the infeasible domain. So I want to be able to return in a short time a set of inputs that is within the constraint bounds and which has a good solution. So when you do that, a typical solution is to use Gaussian process regression or interpolation. So it just amounts to put a prior on your objective function, say. So you said that your response is a realization of a Gaussian process with some mean structure and a covariance kernel. And when you do metamodeling, it just amounts to using the conditional distribution on the observations. You do an initial set of experiments, you run your computer model several times, you get your responses, you condition your Gaussian process by these observations, and you get your metamodel. So this is what I picked you here. You have your observations here. Excuse my French for the graphs. And the gray area and the line is just my conditional distribution. So there's many things you can do with this framework. A lot of people work on the modeling aspects. So the talk we just had was on this topic, how to choose these functions, how to make sure that you infer it well, and how you update it. So that's not the purpose of my talk. I consider that you can do that very nicely. And what I'm interested in is how to use this information to add experiments wisely. So that's the topic of adaptive sampling strategies. Since you have a very expensive black box model, you can spend a lot of time choosing how you're going to sample it. So the principle is to have a sampling criterion. So say your metamodel helps you tell if an observation is interesting or not potentially. So this is why I picked you here. You have your metamodel, you want to minimize an unknown function, you have a small sample, and you build a criterion in red that tells you the interest of sampling in areas. So here we want to minimize, so we have here an interesting region, and especially here, two very interesting regions where the maximum is here. So what you're going to do is sample at this point, run your computer model for 1 hour, update your model, and do it again and again until convergence or budget exhaustion. And in computer experiments, the state of the art is called the expected improvement. So you just use your meta model to find where you can get the best expected gain on the objective, where you're likely to lower your observations sequentially. So now when you consider constraint optimization, so for Gaussian process modeling, there's no problem. You have several outputs. You just use a Gaussian process for each output. It's a lot easier if you do the hypothesis of independence between your outputs for technical reasons, but it's not necessary. So what's the challenge when you have constraints in the picture? Well, first, the admissible domain is unknown, so you have to decrease your objective function, but you have to stay inside a domain that you don't know beforehand. So when you sample, you learn about the constraint, and you learn about the objective function. You have to do this simultaneously. And it's not straightforward. And in particular, when you consider previous approaches, which is just improvement in the objective, it's not really satisfying because you just want to be better at each iteration, but you don't have this learning constraints into account. So in practice, adapting these expected improvements approaches, which are called, I think, knowledge gradient in artificial intelligence, are not really easy to deal with the constraint learning. So what I propose is to use a different paradigm, so stepwise uncertainty reduction for optimization. And the objective of this talk is to propose you a criterion. So I'm not going to talk about proof of convergence because it's too far away from this talk. What I'm only interested in is to find something that is quite efficient to solve my optimization problem, to have some statistical consistency, so to use wisely the conditional distributions, and maybe if it's intuitive, it's a little better. And I want this criterion to give me an automated trade-off between minimizing the objective and learning the constraints. I don't want to tune it. So how to do optimization by stepwise uncertainty reduction? I will first consider the unconstrained case. So the principle of stepwise uncertainty reduction is that it doesn't need to be optimization. You have an objective. It could be just learning, average learning over a design region. And you have an uncertainty measure associated to your objective. So it could be the average variance of your Gaussian process model over your design region. And the stepwise uncertainty reduction is that given your uncertainty measure, you're going to sample toward an observation where in expectation you minimize the best your uncertainty. So that's the whole idea. And the main challenge, of course, is to estimate, without doing the observation, the impact of a potential observation on your uncertainty measure. So that's not straightforward. For instance, you want to add an observation that will improve the best your meta model. So how can you know if it's going to improve or not your meta model if you don't do the observation? Well, you have tricks, and in particular, Gaussian processes are very nice for that because you can do everything by conditioning by the observations. So now let's consider optimization. So you have run some observations. You have a training set, x1, xn. You can get the best observation you found for minimization, which is fmin, the minimum of what you observed. So what's the uncertainty measure associated to that. So you have a couple of previous work on this area. You have people that consider entropy measures. So what you do for entropy measures that you do many realizations of Gaussian processes over a discrete set, and you just look where the minimum of your realization here, and over a large number of realizations that gives you a distribution of your minimum, and you can look at the entropy of the distribution, and that's the uncertainty about optimization in the sense that it's you don't know where the minimum is, and that's a measure of your uncertainty about optimization. So the problem, these approaches are very nice, but they rely on intensive Monte Carlo simulation. So it's quite difficult to use in practice by experience. And you have another type of work, which is where I'm going to base my approach on these ones, which is just to look at the average improvement. I mean, on average, where you can get better, and look at global measure of that. So I'm going to base my approach on these ones with a modification to make it more easy for constrained problems. So let's go back to our Gaussian process model here. You have a set of observations. You have the current minimum, your F-min. And what is the uncertainty associated with the optimization problem when you're at step n here? So we can say that maybe all there is to improve is what's below this line. So that's the probability that your process is below F-min. And if you look at the integral over the design region, you have the volume, so it's the average probability below the minimum. It can be interpreted as the volume of the excursion set below F-min. And that's a very nice measure of the uncertainty you have about your optimization. So if you have a large volume, that means there's a lot of places where your minimum can be. And it has the advantage of being very easy because you can compute it very quickly with Gaussian process model. And more importantly, you can estimate the future volume analytically. So what am I talking about? So let's illustrate here. So you have on the left your Gaussian process model. On the right, the associated volume in gray. And you can compute, if you say I'm going to add an experiment here, you can compute the impact of your uncertainty measure. And you can say that in expectation, the future volume, if I add an observation here, is going to be like this, in the blue curve. So I'm going to reduce my uncertainty about the current minimum. And if you actually do it, you get a posterior uncertainty measure, which looks like the blue one, more or less. And you have a huge reduction between before and after adding the experiment. So we have an uncertainty measure, and we have a way to measure the updates of this uncertainty measure. So we have a sampling criterion. Some elements of calculations. So just very quickly, how we can do that with Gaussian processes. So you have your current integral here, which is the average probability of the process being below the current minimum, conditional on your observations. And your future uncertainty measure is just the expectation when you add a new observation here, Fn plus 1. And what you do is you just plug in the distribution of your current model here. And you do the calculation, and you can get semi-analytical form, so you don't rely on conditional simulations. This is very important. And it's just the integral of the sum of two bivariate Gaussian CDFs. And in practice on an unconstrained problem, you can see that this kind of approach, reducing the volume of excursion stepwise, works quite well compared to state-of-the-art. It's not better than state-of-the-art, but it's competitive. So why bother with a new approach? It's because when you go to constraint optimization, it's very easy to adapt your problem. So if you have constraint, for simplicity, I just have here one constraint, but it's easily generalizable. So you have your objective F, your constraint G, you have Gaussian process priors, and we had previously the volume below F min as our uncertainty. So now we want to be below F min, and we want to be inside the admissible region. So we do a simple modification of the uncertainty measure. First, F min becomes the minimum of the admissible experiments, of course. And instead of having a probability of being better, we have the probability of being better and admissible. So it writes simply as the probability of F being below F min and G below the threshold. So it's very simple. I'm not going to detail calculations, but it's the same idea. Use the same recipes. So since you work with probabilities of being below thresholds, we have update equations to estimate the future probability if you add an observation. So you decompose it to subcases, and you can just get future uncertainty measures. So how does that work? Just a quick illustration. I have here my objective on the left, constraint on the right. In my sample here, I depicted in red the not admissible points. So this one is below the threshold here. So it's not admissible, and that's all I know. So I put my Gaussian process priors, so my model on the left, one on the right, from which I can compute the probability of admissibility. So I know that this point is not admissible. So I have probability 0 to being admissible here. And so I know that this region is bad, but next to it, it's admissible. My probability of being better is probably around this region. So I have the original probability of improvement here, and the probability of admissible improvement is in gray here. So just now a small peak because I know that there's a lot of part I cannot explore. And I can also compute the future probability of admissible improvement if I add an observation here, so which is in blue. So we have now a criterion. So how does it work? So we do stepwise uncertainty reduction. So how are we going to reduce the uncertainty? We can reduce it by 3 ways. We reduce it if the new point is better, then you lower your threshold, so you have smaller probabilities. But you also reduce the uncertainty because you do learning. So you add an observation, your Gaussian process is more accurate, and you reduce your uncertainty. And you do that on the objective model and on the constraint model. And dealing with this volume of excursion, it's all automated. Some particular issues, of course, you need some numerical integration. You need also to have a bivariate Gaussian CDFs to call, so that's expensive. And you're going to maximize your criterion over the design region, so you need an inner optimization. But if you can afford it, if it takes 1 hour to have an experiment, then you can take 5 minutes to choose it. So just an illustration on a toy problem to show you the kind of problems we can address with this. My actual objective function is on the left, and I want to minimize it, so I want to be in the darker green region. My constraint is very nonlinear on the right, and I chose the threshold to have a weird admissible domain, which is in green here. So what you do a first set of experiments. That's my blue triangles here. I have my Gaussian process average that tells me that here is a very nice region. My probability of admissibility by the second Gaussian process that tells me that this is a feasible region, this is an unfeasible region, and the rest I don't know. And my criterion points at a good trade-off, which is the red triangle, and tells me go sample here. So I add this point, and this is the updates. my new Gaussian process, my new probability of admissibility. So I know that I learned something about the admissible region, and my criterion tells me to move and go here. So I do it one more time. I do some updates, etc., etc. And you can see here that it starts looking like the actual admissible region. And after 10 iterations, I have only 15 points here to address this complex problem. I have done some exploration steps. I have done some optimization steps, so I found the actual optimum here. And I have an estimated feasibility, which is not very accurate, but sufficient to find the optimum. So I'm going to conclude here. So I proposed you a way to do global constraint optimization using Gaussian process models by stepwise uncertainty reduction. So I looked at volumes of execution sets, and I reduce it step by step until I have a volume equal to 0. So that means I have solved my optimization problem. And it's quite a flexible concept, and it's very easy to adapt it to constraint optimization. I just change the volume of interest. So it's very easy, and it's automated. I don't have like trade-off with the parameters or something like that. And the fact that I use probabilities of exceedance, so only probabilities of being below or above a threshold, makes it very easy for the calculation. So I have tractable criteria in semi-analytical form because I still have to do some numerical integration, but I don't have to rely on Gaussian process realizations. And in practice, I didn't take time to show you, but that's a very competitive approach compared to state-of-the-art. Compared to non-global approaches for optimization, it's much better, like interior port methods or something like that. And it's also very competitive compared to Gaussian process-based approach that use improvement strategies. And so that's quite an ongoing work because some potential ways to improve it is to look at also at binary constraints. So that's actually a nice problem because a lot of time you have a simulator that is very expensive to compute, and sometimes it crashes. And so that's a hidden constraint. You don't know if you're going to have a response or not. Sometimes you do, sometimes, I don't know, you have just an error in your FEM code. And you can address that very easily with the stepwise uncertainty reduction. You just have to change the definition of the volume of interest. More complex is to look at correlated outputs. It's important because usually when you have an objective and a constraint, they are opposed, they are correlated negatively, but it makes the calculation more complicated. You can look at alternative optimization problems using the same stepwise uncertainty approach. You can derive criteria for multi-objective, for robust optimization, etc. And the next point is convergence proofs. It is, of course, very important. In practice, when you do metamodel-based optimization, there are very, very few proofs of convergence or useful ones. So we look more at efficiency using heuristics instead of proof of convergence. But I think maybe there are ways to do proofs with this kind of framework. And that's the end. Thank you for your attention.
Questions? So what's your experience on how many coverage you can have? So how many parameters you can use in optimization? Do you have some feeling of that?
So it depends on the Gaussian process model you use. For regular ones, I mean, like Kriging models, you can use I use up to 50 covariates.
Mm-hmm.
I think you can push it to 100. It depends on the problem, but you can usually push it to 100, and then you have to use sparse models. And from this this heuristic in particular, you have the additional problem that you have a numerical integration over your domain. So that makes it more limited to, say, 5, 10 covariates.
Yeah, that was what I was thinking about, that this numerical part makes it more difficult. Other questions? Okay, let's thank again.